So we can get started. Yeah. So it's like the 40-minute, including questions.
Awesome. Great. So the next question is quick. Session is short. It's just a single talk, and then we're all going to go into these great roundtable discussions. But we're going to be hearing from Maggie and Makar, and I'll just try to keep you on time. Sounds good.
Thank you. Thanks, Sarah. Sounds like we're good on volume. Okay, so thank you all for coming. Today I'm going to be talking to you a bit about my work, which is causally motivated robustness to shortcut learning. And I want to start the talk with a trend that we've seen a lot. I apologize, it's kind of relatively pixelated, but I think you can get the general look of this graph, which shows on the x-axis year of publication of a specific model, and the y-axis is how much compute was used to train a specific model. And what you're seeing here is this trend of bigger and bigger models. As time goes by, our models get bigger in size, bigger number of parameters, and they need a lot more compute to train. And on some level, this trend has been going on since the beginning of statistical learning theory, of machine learning, of all these fun things. But I think it has kind of, the last few years, it's become on steroids, so to speak. And of course, we're getting more interesting models out of it. We're getting GPTs, we're getting Geminis. It's all very fun and exciting. And also, it comes at a cost. One of those costs is lack of democratization. So as an assistant professor in an academic institution, I cannot train some of these models on the machines that I have access to. That's issue number one that I have with this trend. Issue number two that I have with this trend is it's also not sustainable in a bunch of different ways. But the one lack of sustainability factor that I want to point out is here on the x-axis, you still have time. Again, super pixelated, apologies about that. But on the x-axis, you have time. On the y-axis, you have amount of carbon dioxide and carbon dioxide equivalent gases that are being produced by Microsoft and Google. So the solid lines are the actual production, and the dotted lines are what these companies would need to do in order to reach their commitments of net zero carbon emissions by 2023. The upshot of this slide is that we're getting these fun models, but we're paying a lot for it. They're costing us a ton. So this begs the question, is it true that bigger is better? The upshot of what I'm about to say in this one slide is that no, which is relatively unsurprising. Otherwise, the talk would be very short. But I want to kind of highlight a specific failure mode that these models and this type of scaling doesn't actually solve. And that tends to be a problem that I focus a lot on in my work. So I'll highlight this failure mode by looking at a specific example. And in this example, the authors of this paper were looking at, I want to classify the sentiment expressed in movie reviews. So you see here, the positive movies or the positive movie reviews are written in normal language. But then what they were like normal, they collected normal movie reviews. But then what they did is for the negative sentiment movie reviews, they kind of generated the text such that it looks like it's coming from like a Shakespearean style of English. And what this is doing is it is creating an exploitable shortcut. And by shortcut, I mean these are features that exist in the training data that are spuriously correlated with the target label that we're interested in. So yes, they are predictive, but their relationship with the target label is a spurious correlation that might shift as the distributions change. So they created this exploitable shortcut, and then they used their model. Actually, they used several models. So what you're seeing here on the x-axis is different types of models. And roughly speaking, on this side, you have the biggest model. So you're getting bigger and bigger models as you go along the x-axis. And what they did here, or I'll show you three models. I'm kind of glossing over some of the unimportant details, but I'll show you three different models that they looked at. In the first one, they kept all the movie reviews at training time to be like the original text. So no manipulation or no generation of the text. In the orange yellowish model, they used the positive sentiments were normal, but the negative sentiments, again, at training time, were biblical style. And the red one was this positive is normal, but negative is Shakespearean style. And at test time, all the examples are generated from a normal text. So there's a distribution shift here. And what you see is that as you move from the original, like when the training data is the original data, model's doing relatively well. But as you move along these distribution shifts, there is a bit of drop in the accuracy. And not just that, this drop in the accuracy increases, at least it doesn't go away when your model size increases. So the takeaway from this slide is perhaps scaling is not all we need. Building larger models does not always give us robustness to these shortcuts. And what I'm going to try to convince you with in the next 35-ish minutes is that one of the best tools that we have access to address these issues of shortcut learning and lack of distributional robustness is this causally motivated regularization approaches. So causally motivated regularization approaches are regularization methods. So by virtue of being regularizers, they give us, or we expect them to give us some kind of efficiency, where we may be able to escape that aggressive scaling up and increasing in model sizes if we are to use this kind of regularization. But importantly, they are causal. And by causal, I mean they encode some, or they encourage the model to encode some notion of a causal mechanism that we believe is true, that we believe underlies the true data. Go ahead.
Training data, or you talk about compute time? Each of them is a different coordinate.
Yes, what I'm going to focus on today is data size. So I'm going to talk about like statistical efficiency, but the question you bring up is something that I've been starting to think about a bit more, which is I want to now think about computational efficiency. Can I show you that my model converges faster if you use these tools? That's very much kind of what I'm right now thinking about. But everything that you're going to see here is going to be statistical efficiency. So roughly for the same budget of data and the same model, roughly speaking, model architecture, I'm going to give you a better accuracy and robustness. So yeah, does that answer your questions? Are we happy? Okay. All right. So they are causal in the sense that they will encourage my model to conform to some causal mechanism that I believe is true, and that I believe kind of generates my underlying data. And because of that, it will give us some notion of robustness. So a core idea here is that the causal discipline, or causality and causal reasoning, tends to reason about what happens to the world as I intervene on it, as I change something in it. So this notion of shifts is very core to the causal discipline. And I think that's why it makes it particularly suitable to think about these kinds of robustness properties, or that's why it gives us these robustness properties. Okay, so time permitting, I'm going to talk about three pieces of work that I did. I should say this, I designed this talk to be kind of like a Lego. If we spend a lot of time in one piece, I can just like swap out another with it. So please feel free to interrupt. It's generally going to be high level, but I'm very happy to kind of like pause it and go deeper into one of those things. I'm going to talk about three different works that I've done. The first one looks at what happens if I know, can I build these robustness if I know what the source, what's the shortcut? The second one will look at what happens if I don't know what the shortcut is, but I still want this robustness. And the third one will look at some very, very first steps that we have taken in the context of shortcut learning for language models, let's put it that way. Okay, so starting with the first, I should also say that a lot of my work is motivated by applications in healthcare. So a lot of the examples that you will see today are rooted and grounded in healthcare applications. Okay, so let's say that I want to build a model to detect pneumonia from chest x-rays, and I believe that was one of the things that Zach said we should not do. So that's what we're doing now. So if I have some data set, and this data set, I was looking for you. Okay, so if I have some data set, and this data set is x-ray images, and at training time, I have my target label that I'm going to want to predict, which is whether or not the image has pneumonia. So does this patient have pneumonia, yes or no? And Y takes on a value of 0 if the patient is healthy and 1 if the patient has pneumonia. And only at training time, I'm also going to assume that I have access to some auxiliary labels, and that here is the sex of the patient. So this variable, this auxiliary variable, takes on V is equal to 0 if it's a man, and V is equal to 1 if the patient is a woman. But in this setting, we're going to look at situations where there is bias sampling. So at training time, I do not observe many women who have pneumonia. So let's say this is taking place in some county where women are too busy to show up to the hospital when they have pneumonia. So by the time they show up, it's like respiratory failure, and they don't get this pneumonia label. And just for the sake of symmetry, I'm also going to say that I'm not observing many men with who are healthy. But this symmetry is not something that's necessary. It's just for convenience. And what we've seen here is if I take this data set and pass it through some deep neural network, what I end up with is a model that knows how to detect pneumonia in men, but for women, it's unable to detect pneumonia. And again, what we say is happening here is shortcut learning, meaning the model has learned to encode something like the width of the chest or the presence of breast tissue as a predictor for pneumonia. So it's an entirely spurious feature. It's not biologically men and women don't have any differences in risk of pneumonia. So it's entirely spurious. Okay. And then here, the question that we are going to ask is, can we build models that are robust to learning this shortcut? They do not learn this shortcut. And the way I'm going to do that is by first viewing this problem through the lens of causality. And what I mean by that is we're going to impose some causal assumptions about the data that we're observing. Go ahead. Yes, please.
If I know what's the cause of pneumonia, then it's a shortcut. I just look at this and don't look at the width of the chest.
Yes.
So what you mean here is only spurious shortcut.
Yes, exactly. Yeah. By definition, a shortcut is a spurious correlation. I'm going to kind of formalize that a little bit more now. So maybe if after this slide, that's still a question, let me know. Okay, so the causal assumptions that I'm making here are one way to talk about these causal assumptions is through what we call a causal directed acyclic graph or causal DAG. This causal DAG has every node is a variable and every edge is a possible causal relationship. So in here, the example that I've been giving, I've already introduced Y, which is our target label, that's pneumonia. V is the auxiliary label, which is the sex of the patient. And we have that Y causally affects my inputs, which are the X-ray pixels, through this X star. And you might not be able to see it. Maybe it's more obvious on the monitors, but we have that Y, V, and X are shaded, so they're gray, meaning they're observed at training time. X star is not observed at training time, or we don't measure it explicitly at training time. And you can think of it as a sufficient statistic that summarizes the causal effect of Y on X. So for example, it can be, if pneumonia presents as blotches on your X-ray, then X star is blotches on the X-ray. And all these arrows are causal in the sense that they are fixed. It doesn't matter where I'm sampling my data from. These relationships are biologically true, so they are not going to change. But also there's this dashed bidirectional arrow, which encodes a correlation, but not a causal relationship. It says that there is some spurious correlation between the sex of the patient and the target label, which is pneumonia. And the problem is that this correlation varies. Meaning if I sample from hospital A, maybe here, women who have pneumonia are underrepresented. So that's one possible value for this correlation. But if I sample from hospital B, maybe the correlation is completely flipped. This correlation is not biological, it's not fixed, it changes. And this causal lens, I personally find it helpful because it allows us to formulate the task with a little bit more concreteness. So our task here is that we have some data that expresses some spurious correlation between V and Y. And what I want is some predictor f of x, and I want this f of x to be accurate. But I don't know where my test distribution is coming from. It can encode any possible correlation spurious correlation between the sex of the patient and pneumonia. So not only do I want F to be accurate, I also want it to be robust to the shortcut, meaning I want it to have the same performance across all possible correlations between V and Y. So that's our task formulation. Not only does causality here help us kind of have a concrete formulation of our task, it also helps us understand where this shortcut learning is coming from. So if you look at this causal DAG, there are two pathways between X and Y. So I'm taking X as an input and I want to predict Y as an output. There are two information pathways between those two variables. The first one is the green variable, and this encodes all causal relationships. So this is like the good path. But also there is this red pathway, which encodes some information. It passes through this correlation that we don't like. So it encodes some information about the correlation. So that pathway is not robust. So we're able to categorize exactly where the bad flow of information is. And our first result was that we can, by analyzing this DAG, we can get some population level robustness. And specifically, we get that because there exists an ideal distribution. And that is a distribution where there's no correlation between V and Y. If I am lucky enough to sample from this distribution, and if I sample enough that estimation error is not a problem, then we get the result that our empirical risk or population risk minimizer is actually robust to the distribution shifts. It's robust to the shortcut. I just said two crazy things. Go ahead. No.
These are, I mean, you didn't define causality in any other way, just to say it's invariant to my different.
Okay, yeah.
But invariance is something you can never tell about the next population that will come up.
Yes, I think the difference here is that I'm saying invariance is born out of a set of causal assumptions that I'm making.
That's the only thing you can measure is the invariance, because how do you?
Yeah, that's fair. Yeah, it is that's fair in that, like, I cannot, rather, this DAG is an assumption. Like, by assumption, this is true. Can you measure it? There are approaches that do causal discovery that actually will come into play in the next part of the talk. But right now, this is by assumption. And by assumption, these relationships are causal in the sense that by assumption, they hold across distribution shifts, or the parts that are varying, they vary. So yes, this is an assumption.
I guess a follow-up question to this is more, do you need to make this assumption at all?
Yes.
Since maybe the invariance could be discovered by just saying, out of all the good predictors, which one seems to be doing well on both populations?
Oh, you're assuming that you have access to two populations. I'm not assuming that. Meaning populations of that have that express two different correlations. No, I'm not going to assume that. But I think the point that you're making is also interesting, and I want to kind of respond to it a little bit more. And I think this goes back to something that you said you said in Zach's talk, is that when we talk about things in the abstract, yeah, there's a lot of impossibility. But when you scope down the problem, when you say, here are my specific causal assumptions, there will arise from those specific causal assumptions some invariance properties that we might be able to carefully exploit. But one thing I'll say is that these causal assumptions are important. Like, without them, the stuff, or if you change them just a little bit, the stuff that I'm about to say changes dramatically. For example, if there is a true causal relationship between V and Y, so sex observation actually does affect Y, the stuff that I'm about to say will give you a biased estimator. So the point that I'm making here is that the specific causal assumption that we're making give rise to specific invariances. And small shifts in those causal assumptions are important and necessary to carefully reason about. And I don't mean to pick on Zach anymore, but I do not ascribe to the idea of, like, I'm going to create one general solution that fixes everything. I just don't know how to make progress that way. I like to kind of be grounded in, here are the specific assumptions that are correct or relevant or appropriate for the specific problem. Go ahead. I don't at all.
So I guess the question for me more is, who is supplying this causal graph?
Yes, that's also a really excellent question, and it kind of, I'll pump back to the question, but I mean, a lot of the work that I do is done in collaboration with actual clinicians who do tell me, no, we do not expect women to have any like increased risk of pneumonia or reduced risk of pneumonia biologically. So if you're seeing that, that's off. And I do think that like these nice, well-scoped questions are often not born out of individual research. It's more like interdisciplinary work. There, I feel like you have a question and I want to hear it. I want to hear it. Yeah. In this example,
and can I say?
Yes, please.
Compliment what Shai said.
Yeah.
When Shai said generously what the doctor knows, really what he means is what the doctor thinks.
You know, or he or she knows, yeah.
He or she knows.
Yeah.
And that actually the whole notion of causality, as many people discuss, might just be a view of the mind. It might just not even exist. So.
Like the notion of something that is causal is a view of the. Well, but what if you? I mean, this is not what I'm gonna do here, but in general. No, I mean what
I want to raise even more.
No, this is great. I love it. I think.
What is the reason that Trump won?
It is incredible how I've been trying to avoid elections as much as possible, and here I am. But okay, I want to.
Interest of time.
Okay, keep going. All right. I mean, we're on the elections now. This is getting it's getting good. Yes. Okay. So yes. So the last thing that we reached here is that there exists some ideal distribution. And if I'm lucky enough to sample from this ideal distribution, and if I sample enough such that I don't need to worry about estimation errors, then then the population risk minimizer is a robust model. There are two crazy things that I just said that should make you skeptical. One is, what if I sample from the ideal distribution? In a lot of cases, I will not sample from the ideal distribution. And the second thing is, well, what if I sample enough such that I have no estimation error? That also should make you skeptical of what I'm about to say. So let's relax those two crazy assumptions, and I'll do that in the next couple of slides. So first, let's relax the assumption that I am sampling infinitely many or enough samples that I do not have any estimation error. And what we found is that models, I'm going to keep the ideal distribution assumption for a little bit, but I'm going to relax it in a second. What we found is that models that conform to the causal DAG are more efficient than the usual models in finite samples. Now, what do I mean by that? Usual models are models that minimize some prediction error, and they place some constraint, let's say an L2 penalty, on the weights of the model or on the capacity of the model. By models that conform to the causal DAG, I mean these are models that do not encode a relationship between V and Y, because remember, we're sampling from the ideal distribution. Another way to say that is that I want the probability distribution over the predictions for men to match the probability distribution over the predictions for women. In practice, there are different ways to do this. The way we're going to use is we're going to minimize the prediction error, and we're also going to impose some penalty, and this penalty is MMD, the maximum mean discrepancy, which measures distances between two distributions. If you don't know what the MMD is, you can think of it as it compares infinitely many moments of the two distributions with some bias on, like it prioritizes matching the lower moments of the distribution. Black box it as this is a measurement of the distances between two distributions. And I want to give you a sense of like how we arrived at this result through a simple example. So this is a very kind of as simple as it gets. In this example, my input, is just two variables. One of those two variables will encode information about the shortcut, that's the bad variable, and the other encodes information about the target label that I'm interested in, so that's the good variable. But the important piece to keep in mind in this simple example is that I don't know which is which. And to keep things even more simple, I'm going to say my model is a linear model. Again, it does not get any simpler than that. And I don't think I need to tell this crowd this, but I'll just say it. A helpful intuition here is to think about model learning as a search problem. I'm going to define some search space. And then I'm going to search within that search space for my optimal model. So what I'm going to draw here on these axes, if you can see them, I don't know, is all the possible, I'm going to kind of illustrate different search spaces. So on the x-axis is all the possible values that the coefficient for the bad shortcut can take. And on the y-axis is all the possible values that the good variable can take. And in an ideal, oh, wow, this says ideal unattainable, it's super pixelated. Again, sorry about that. So the ideal unattainable search space would be this red line. It's nice because it sets the coefficient for the bad variable to be 0. It's unattainable because I don't know which variable is which. If you do L2 regularization, you end up with a function space that's significantly better, that's significantly bigger rather, not better. The fact that the L2 space is a lot bigger than the ideal search space is not good because now our search space is bigger. It's a harder problem. Now, if you do this causally motivated regularization, you end up with some search space that kind of looks like this blue oval. And the more, roughly speaking, the more you regularize your MMD, the more squished this oval looks like. I mean, if someone's interested, I'm happy to go over the details, but we show in the paper that this leads to a smaller upper bound on the Rademacher complexity relative to the L2 regularized models. Okay, so that's, we're no longer looking at, we relaxed the assumption that I have infinitely many data points, and we looked at finite samples, and we found that we get some efficiency because of this causally motivated schemes.
What is the regularization here?
So the regularization is the MMD. Yeah, so this is the MMD regularizer. It just says whenever the distance between those two things is non-zero, penalize the model. Is that good? Yeah, okay. Okay, so recap. If I have the ideal distribution, I have a large sample, then I get robustness to the shortcut. If I have the ideal distribution, but I don't, go ahead. Happy to.
From the ideal distribution without the penalization, you would have gotten the right model.
Yes, but here you're thinking about the search space. So when I'm trying to quantify the hardness of the learning problem, it is still possible that you end up picking a non-zero weight for your bad, even though unlikely maybe, but it's still possible. It's still an option. Go ahead.
Process that you're considering, for example, are you considering linear models in this result? Or?
For this simplification, yes, it's a linear model, but in general, like in the paper, it's a more general argument. So no, it can be like you can use some of I'm gonna forget the first. I don't remember the first author's name, but Sasha Rocklin has a bunch of like different papers that you can like use even those simple linear models to get a generalization bound with respect to like a multi-layer or multiple layer depth neural network. So these are very generalizable, I think. Good question. Other. Okay. So ideal distribution on large sample, we get robustness. Ideal distribution, but small samples, we get efficiency. If I am sampling from an arbitrary distribution, if you do what I just said, you will get actually a biased model. So your oval will not include the ideal model. It will be overly conservative, and obviously you might not get robustness to the shortcut either. Okay, so what do we do with this? We go back to ideas from causality. In causality, we often have a notion of an ideal distribution that we would like to sample from, which is a distribution of a randomized control trial. And we have these fun reweighting schemes that we can use so that we can statistically mimic a distribution that looks like the ideal distribution. And that's exactly what we did here. We designed a set of weights that map us from any arbitrary distribution that has an arbitrary correlation between V and Y. And we use those weights to reweight the data such that it mimics the nice independencies that we get in the ideal distribution. So this reweighting helps us recover the ideal distribution. And I'm not going to go into the details of these weights, but This is basically the distribution. It's a ratio between the ideal distribution where there's no correlation between V and Y and the observed distribution. And obviously there are like some really nice classical results about how these reweighting approaches inflate your generalization error. And we kind of use these to inflate our like you will incur a little bit of cost when you're using these weighting schemes. Go ahead.
Patterns or uncorrelated?
You recover the fact that V and Y are independent of each, like the spurious correlation does not exist.
Are you assuming any linearity anywhere?
No. Linearity between what and what, maybe?
Like unobserved U and Y.
No. Okay, how about this? Let me show you the objective function that we used, and then if you still have that question, Tom. All right, cool. This is the objective. Okay, so we're going to minimize some weighted prediction loss, and also the MMD has to be weighted. So I'm reweighting the distributions and measuring the MMD between them. And just to recap, the causal perspective gave us these weights in order to recover the specific relationships that we want to hold between V and Y. And the invariance penalty encourages the model to kind of encode the desired independencies that are expressed in under the ideal distribution. Go ahead.
Importance weighting, no?
Yes, exactly.
In this case, these importance weights, they don't need to be estimated.
In a very simple setting, this is going to be like a 4x4 matrix, because you have like you're counting, if both are binary, it's super simple.
So that depends on your DAG.
It depends on the specific variable types. But I guess generally everything that I'm saying will depend on the DAGs. That's there.
Size of this.
Yes, I might be touching upon that in a second too. Okay, so I'm also going to do something that Zach said we should not do. I'm going to evaluate our models on a specific toyish data set. Don't look at me, Zach. I'm going to evaluate on a data set that is semi-simulated, where we superimpose images of birds on background. So the task here is I want to predict the type of bird without using the background as a possible shortcut. So my label is bird. At training time, I'm going to fix the distribution such that the majority of water birds appear on water backgrounds, the majority of land birds appear on land backgrounds. And I use this word majority. Like I'm careful with what I'm saying. It's not all, it is the majority of examples. And at test time, I'm going to evaluate by simulating multiple different distributions. And each one of those distributions will kind of encode a specific correlation between V and Y. Okay, so let's look at the results. On the x-axis here, I have the correlation at test time. So what is the correlation between the background and the bird at test time? And on the y-axis, I have the AURC again at test time. And this dashed line tells you where the training distribution is coming from. So at training time, the probability of background given bird is about 0.9. And we'll start with looking at how our model does relative to a typical deep neural network, which is a neural network that kind of imposes some L2 penalty on the weights. Okay. So obviously, our model does. This is I think what Victor called the token machine learning paper result. Our model does better than the comparator at every possible distribution shift, which is to say our model is able to not rely on the shortcut better, or is more robust. Before declaring victory, let's look at the two components that we introduced here. Can I do an ablation study type thing? So gray here is the weights, weighted only, meaning I'm only reweighting using these important sampling methods, and I'm just minimizing the loss. So that's the gray line. It does a little bit better than the deep neural network with only L2 weights, but it's still not kind of realizing the full potential. Now, this other model does not use the reweighting. So it looks at the data and it says, I just want brute force, like I do not want my predictions to have any information about the sex of the patient, independently of where the data is coming from. dependently of what correlations exist in my data. In this case, the model ends up being overly conservative because it is regularizing out a correlation that should exist according to our causal DAG. So in other words, both components of our causally motivated approach are necessary. How much time do I have? I lost. Oh, okay. All right. Here's what I'm gonna do. I'm gonna tell you, go ahead, Zach.
5 years ago.
Can you say that again?
People do importance sampling, importance weighting
Yeah.
with deep neural networks all the time because it's like we're just in the habit of applying importance sampling, importance weighting in certain kinds of problems.
Can I say something?
Yeah.
Watch how well I know Zach. Are you gonna ask if the training error is 0? Does this matter?
Well, getting there, but basically broadly, like as you train longer and longer, and certainly as you approach the regime where you get towards training errors. The findings that we had was that the effect of importance sampling, if anything, starts off strong and disappears completely.
Yes.
Whether or not importance sampling is doing anything as like a weirdly contingent on like when did you do early stopping?
Yeah.
And so like curious if you're doing importance sample weighting in the context of deep neural networks, like
Yes.
how do you navigate this? And decide when to stop?
Yes, I remember we looked at your paper when we were doing this work and like, why are we not seeing that? I think maybe. So, okay, there's also a regime where if you're achieving 0 training error, like all your examples of 0 training error, you really don't need weighting at all. Like that's entirely useless. My sense is that both these patterns will only arise in settings where your model capacity is large enough that you can do this like interpolation or whatever we're calling it. I did not see that when I was doing this work empirically, but it's possible that there are specific regimes, and I think it's specific dynamics of the stochastic gradient descent, of things like that, which you kind of alluded to, that might make these weights not useful or maybe sometimes harmful. But this is getting at, I think, what I was saying earlier about I would like to start studying a little bit how these types of approaches affect your training dynamics, and I think that's the core question. Go ahead.
Quick
Yeah.
comment on importance weighting.
Yeah.
It's known that when the second moment is too large,
Yeah.
it ruins basically.
Yeah. Yes.
This has been analyzed.
Yes. I'm familiar with some of Professor Cortez's work and things like that. Yes. So I started actually this work by thinking this was more or less the starting point of this work, and we were asking, how do we make the variance lower? And so the way I presented is not actually the way how I thought about it. We started by saying, okay, importance weighting, let's do that. That should fix things. And then you start running into these issues of very unstable weights. That's why we overlaid the kind of the regularizer on top, because that was our way of trying to control for the variance, especially in cases where the weighting, the way I presented it doesn't present the thought process that way, but that's how my brain thought about it at least. Okay, I think what I will do is I'm gonna go through this one slide and then we'll stop more or less there. So the second part of this work was work where, let's say I don't know where the shortcut is. I have a bunch of metadata that come with an image. Every image has a bajillion labels. Some of them might encode some shortcuts and some of them are not. So we don't know which ones are relevant shortcuts and which ones are not. And our objective was still, we want a model that is robust to any possible correlation that exists in the system, spurious correlation. So the upshot of this work, which I will not have time to go over, is that we need to do a causal discovery step first. And that might be, I think, what both of you were trying to get at earlier, is that you will never be able to learn more. No, there are some causal discovery approaches where if you impose enough assumptions, and it's an assumption game. So if you impose enough assumptions, whether it's about the functional form, so you're not only, you're no longer allowed to make entirely non-parametric, everything can be non-parametric, you have to like constrain your function space a little bit. Or if you constrain certain relationships, so you start with a completed partial directed acyclic graph, meaning not, like you have the skeleton there, but you don't have all the edges, you might be able to learn something about the relationships that maybe even the clinicians don't know. Unfortunately, I won't be able to go through this, but I'll, here, this is you missed a big show y'all. But I am around if someone's interested. I'm more than happy to chat about these things offline. Okay, so where I'll end is, I talked a little bit about, I guess, 1/3 of the causally motivated prediction approaches, but I just want to end on causally motivated prediction is just one, I think, in my opinion, one set of very interesting questions that we can be asking now. But we also have looked at especially problems in offline reinforcement learning through the causal lens. And we were also able to see that you can get generalization error, improvements in your generalization error, and you can get even better uncertainty estimation if you put that causal lens on. Another area that is newish to me is looking at distribution shifts that are not just because of these naturally occurring distribution shifts, but also because an agent is trying to manipulate the system such that they get a better payout of your model. So what does causality have to do or have to say in these settings? I encourage you to find our paper in the upcoming NeurIPS, and I will stop here. Thank you so much for a very lively conversation.
Like consistently throughout, but I think we have time for maybe 1 or 2 questions before we go to lunch.
Go ahead, Rich, or I don't know. Can we do 2?
Yeah, we can do 2.
Okay, someone go.
Is there a reason why you chose MMD as the distance between?
Oh, excellent question. I love it. I think in general, you could probably use something like KL divergence, something like that. It just, in this case, using the MMD gave us an easier way to prove the thing that we wanted to prove.
The efficiency.
It's the efficiency, and there's actually a structural risk gap that I didn't go over. That I'll just say this: the MMD it minimizes distances under a very nice and well understood, or the MMD when it's defined with respect to the RKHS, it gives us very nice constraints that we can then play with in ways that were useful to us.
Characteristic, because I imagine every MMD is associated with the
Sorry, can you speak up just a little bit?
sorry. I imagine every MMD is associated with the RKHS.
Oh yes, that's probably true. Yeah. It's probably true. The one that I played with in this setting was RKHS, and it's nice because it's like very well understood, and we have a lot of really great work that kind of characterizes different things in that space. Okay, Rich.
So it's a question about, one is the comment about causality. So thinking that the MMD constraint can also be thought of as an invariance you'd like the model to achieve, right? And so trying to match that. But then the question is more about what happens in the real world when that invariance doesn't actually reflect what's in the real world? And that might be something that you'd like to do, but and so I was interested in your experiment where you said, if at training and at test, they both had this, was at the 0.9, right? You'd expect the neural net to outperform something with the MMD regularizer. In your experiment, it didn't look like it did. So I'm curious as to why in the real world, if the invariance isn't quite present, right? And when would you expect the MMD to improve on things?
Yes, if the invariance is not, I think what you mean is, or correct me if I'm wrong, if this invariance is incorrect, it is inconsistent, yes, then you get bias.
Yeah.
Then your function, the best possible function is outside of your function class. You're regularizing the wrong thing. So you will get an overly conservative estimate of your model. It will definitely be outperformed by other.
But in your actual experiment, it looked like that didn't happen.
Yeah, because the experiment is designed so that my assumptions are correct.
You varied the amount of the invariance, I thought, that was present at training and at test. When they matched.
When they
They
matched.
were at 0.9. I thought that was meant that what happened in the test was the same as what was in.
Yes, and yes.
So that's.
Here. I was really good at ending on time, but I think
There's no other.
I think I'm entitled.
Okay.
Yeah, I have you guys
Yeah,
hostage
that
now.
was it.
Oh, wait, here it is. Yes. So you're saying
No, not the actual experiment.
yes. I'm going.
Your obligatory
there it is.
result.
Yes. Yeah. This nice result.
Right.
And you're saying in distribution, it looks like it's doing better because in general, that might not be true. And okay, I have some other results on a different data set where you see that everything that's beyond this line, you're actually like your invariant model must necessarily perform worse because the shortcut has information.
Yes.
And in every distribution that's outside of this, exploiting the shortcut actually is a good thing. Yeah, like you want to do that because it has information. I guess they're kind of equivalent here, but in general, you might see that drop.
Thanks for an awesome talk.
Yeah, just, hi everyone again. Just looking through, I just look quickly